Excellent. So this is the what we don't measure but should in data science. There's no time to explain edition of the presentation. So we'll jump right in here. Basically, I'm going to go through three different factors that I and coworkers have been working through over the past year and think, oh, these are things that really aren't codified in any meaningful way in the typical data science modeling process. And we really should start to think about these more deeply. First of these being something that we're going to just colloquially refer to as type Y error. And why type Y error? I'll talk about this in the context of a specific real world example. So in 2019, there was a lot of news articles published about a study that was written about a healthcare algorithm furnished by a company called Optum Healthcare. And what this study found was this healthcare algorithm, which was furnished to hospitals throughout the US and was meant to kind of triage patients and determine, hey, given a certain set of patients within a population, which of these patients most needs care, it was found to be biased against African Americans, at least relative to patients belonging to other ethnic groups. And while this was likely unintentional, it came as a result of this quote unquote type Y error, where Optum was saying, okay, we're going to predict your future need, not as some direct function of your bodily function or something really related to your healthcare needs, but of your expected future healthcare costs. And encoded in that outcome was your ability to access healthcare in the past. And as we all probably know or have some inkling of, healthcare and healthcare services are not distributed evenly throughout the US. And a lot of African American patients did not have a strong prior history of healthcare expenditures. Ergo, there was not a lot of predicted healthcare need in the future, despite them having a high need. So this is the importance of getting a correct problem specification. You want to minimize type Y error, quote unquote, by specifying the right outcome and modeling the right outcome. And we can look at this through three main ways. First, carefully considering what outcome you wish to measure should be pretty straightforward. Not using proxies to that outcome if possible, because they may not be as correlated to your outcome as you would expect. In this case, future healthcare spending was not as well correlated to current healthcare need as Optum expected. And finally, if you can, if the resources and time permit it, build a toy model and examine the results of this model on training data and a subset of your test data to see if problems like these kind of come out. Because you want to be able to identify issues like these before they get deployed and you and your company end up on the next MIT technology article about failures of AI. So next thing, predictive fairness. We want this because we've seen what happens when we don't have it. I think one great example of this is the case of the Compass recidivism data that ProPublica wrote about, I think in 2017. I might have the year plus or minus 2 years off. Basically, what they found is African Americans were in this model. I'm sorry, I'll back up. So the recidivism task in itself, the model was predicting, okay, for someone who we know is a criminal who's committed a certain crime, the model wanted to predict whether or not they're going to commit another crime in 2 years. So binary, yes, no. The model had a slightly higher error for African Americans relative to other groups. Not much higher, but slightly higher. And what ProPublica found was, this error was present, but it wasn't just the fact that this error was there, it's that the actual direction of the errors were different across groups. So when you actually composed false positives versus false negatives or decomposed that, African Americans by the model were predicted to have a much higher chance of recidivating than members of other groups. And what this led to is a lot of African American defendants being held on bail when they weren't going to commit a crime in the future, versus a lot of, say, white defendants or defendants from other racial groups being let out despite the fact that they would go on to commit crimes. And this is all stuff that could have been recognized if the people doing this analysis or the people building the initial Compass model I can't remember the name of the company off the top of my head, but if they were looking at the performance of their model across groups. So lessons here, don't trust single overall metrics. You want to look at groups. Calculate model performance across different groupings of the data. If relevant, not all modeling tests have groupings that are, sensible or you can easily kind of calculate across, but if you do have those, do calculate those performance metrics across groups. And then finally, examine the error direction and relative error across groups and not just overall error, because again, even if you see that one group has higher error or lower error than another, it may mask the fact that most of that error happens in the false positive realm or the false negative realm. And that could be very relevant depending on your task. Finally, differential impact. And this is the one that I've consistently had the hardest time trying to explain. And I think that's been true with basically everyone who's tangling with these issues, but I'll try nonetheless. So I probably should have got a better image here, but I think the best case to really explore this is through facial recognition positives, and false positives, true positives, doesn't really matter. One really indicative example, I assume people by now have heard some news about the treatment of the Uyghur people in Xinjiang, China. So this is an ethnic minority which is really heavily surveilled and policed by the Chinese state, and their ability to travel is heavily restricted. So what will often happen is they have to get very specific permissions or very specific allowances by local Chinese government officials to travel anywhere outside of Xinjiang. And any airport or subway, what have you, train in China is likely to use facial recognition to match you with a ethnic group or do a direct match against a criminal database.
45-second warning.
Not a problem. And if you are matched here as a Uyghur person, you're likely to be treated much more harshly, regardless of whether the match is true or false, relative to a Han Chinese person, because you're much more likely to be suspected to be a terrorist. So even if you get the same prediction, depending on the group, it may differ entirely in how it impacts them. Something to keep in mind. So that's the kind of importance of follow-up, seeing what happens after you make the prediction. So here, consider failure scenarios during the design phase project. Ensure that SMEs and or affected groups are consulted in the design phase, because they're going to likely be able to tell you whether these differential impacts are likely to happen. And then finally, monitor your model closely, because once it's deployed, this kind of issue may crop up and you're going to need to be able to kind of respond nimbly to address it. And yeah, that's really all I had here.